So we're back for part 3, looking at actually some multiomics integration, which I kind of promised was the main topic of this, but you do sort of have to start from doing one before you can do many. And yeah, so we are going to be working off lesson 3 materials now. So this is going back to the homepage. You can look at the full text here with a lot of nice text if you want to read about a little more of the background of what it is we're doing. Yes.
I just have like more of a conceptual question.
Go for it.
So like let's say you skip the first 2 parts, just the DIABLO integration. What like would be the key things that you'd be missing?
Yeah, I mean, I feel like the DIABLO is very, I mean, I think you could get similar, hopefully, individual features that were important in the DIABLO would also be important if you just looked at each of the omics in isolation. So it might be okay to go directly to it, but I think looking at the individual omics is, at least, you may not have to do like the differential expression analysis on every single one, but at least looking at each one and doing the transformation and visualization of the data is, you're going to have to do that before you can't go straight to the multiomics integration. Yeah, so I think, right, the idea of doing the multiomics integration is to see whether there are patterns within that cut across all of the omics that explain the outcome or or are associated with the treatment of interest versus just within one. So it's really just kind of like an extended version of that. So yeah, you don't really have to do, I would say, the individual, but DIABLO is not looking at differential, like significant cutoffs of differential expression in any one variable. It really only makes sense to do that within each omics data set at once. So if that's anything you're interested in, you would go like, DIABLO is not as much about p-values. It's more exploratory. It's trying to draw pretty pictures and tell stories off of the data set. Yes, there are ways to like formally test things, but it's more descriptive and it's more exploratory. It can be used as a predictive model as well, which we'll talk about a little bit. So yeah, does that help explain like the difference between them? Yeah. So here we are. There's the full text. If you're doing this on your own computer, not on the demo server, you'll need to pull down the worksheet from here. So let me go back into Posit Cloud demo server. I should have made this full screen before to get a little bit bigger. So I'm going to go ahead and close out the worksheet from last time. And I'm going to clear the console. I'm going to use this room thing to delete the variables from the environment because we're not going to need them anymore. And then I'm also going to restart R. All these things are good practice when we to start with everything fresh, no packages loaded, and no objects in the workspace, just to make sure we get the same, the most consistent results. Now, I'm going to go to the worksheets directory in the files tab over here. If you're doing this on the Posit Cloud server, and open the part 3 worksheet. And so let's go ahead and run the first few lines to load the packages that we're going to use and define our colors so that all our plots look consistent. And we're gonna use the mixOmics package, which we haven't used yet. So if anybody is doing this on their own, just let me know. Give me a thumbs up if that loaded without any errors. Do you have that installed? If not, we'll have to make sure you get it installed. It gives you a lot of information about packages that are loading, but if you get some angry red text, that'd be bad. So if everyone's good and has mixomics installed, and so I'm assuming everyone's good. And the next thing we want to do to make sure that everyone is good to go is import the data. So these are all the pre-transformed data, the log2, log transformed, and Z transformed. In other words, standardized data. So this is, everything has been, and I'm not sure if it is Z transformed, but it's definitely log transformed that we're working with. And also, I'm loading this pre-tuned model. This is not something that you would do in reality, but the model cross-validation takes a really long time to run. Like, it took more than an hour on my computer, so I didn't want to make us all sit here and wait for that. So I just did it and then saved the preloaded object just to save time in the lesson. That was why I did that. But that's not something that you would do in practice, obviously, because you wouldn't have the model output yet. So I'm going to highlight that and run all that. If you're doing this on your own machine, you're not going to have that data folder. So you would just uncomment all these 4 lines here, uncomment them and then run them, and it will load them from, it will import them from a website. So you'll need to do that 4 lines, each one of the three omics data sets plus the pre-fitted model. So we'll give everyone a second to get caught up there. Yes.
I actually did get an error when I tried to look at.
Okay. Let's take a look. The mixomics one.
The mixomics, no, that one worked.
Oh, it's still the mouse one.
So should I just use the online?
I see. Well, you can try to install it again.
I thought it installed yesterday.
Again, you try that.
I don't know. Okay.
Well, we can try it one more time, just
Did I get over?
for fun. Here, I'll just type it in for you real quick. You're good. Thanks. One.
No, I'm the only one.
It's not like essential to have it, but it'll just make it easier and then you have to like change that. Yeah, you're running it a little bit.
I think this is something. No.
Well, just let me know if that does anything after a minute. It's taking a minute, but. So we'll just give it a minute for everybody to get caught up. So yeah, then once you have the libraries loaded, then you would import the data either from this local folder or you can uncomment these lines and run them to get it from the website if you're doing it on your own. And the next step is basically, so we've already gone through the individual omics and we have kind of like done all the filtering, we've done all the transforming, everything is like in a form that's ready to analyze. So we don't have to do a lot of pre-setup steps at this point. All we have to do is get the data into a format that can be inputted into the DIABLO function. So once we get to that, I'll go over again exactly what it's doing. But for now, we need to know that that we're going to need as many N by P matrices as we have omics, and we're going to put them in a list. A list is like a we have a list of objects put together that are combined into one object. And you can see that when we imported the data, it's all in a P by N format. And we want N by P. We want the 18 rows and a lot of columns instead of 18 columns. So we're going to transpose them all. And you can see, oh, this is also just good to look at. You can see we have our metabolome data has only 171 different metabolites, and that's typical. Metabolome data usually has much fewer features than things like transcriptome. Obviously has way more, since there just aren't as many different metabolites floating around as there are genes. Not to mention, it's expensive to get very wide metabolome data, so usually they're much smaller numbers. So yeah, we're going to do that, and then we're going to give each element in the list a name, which is helpful because that will show up on the output and the plots and stuff, so we'll know which is which. We're going to call them transcripts, metabolites, and proteins for each of the 3 omics. You can call them whatever you want, but that's what we're calling them here. And we're going to first use the T function to transpose, so that we have our 18 rows each time. We're going to use na.omit, get rid of any rows that have missing values in it, which I'm pretty sure none of them do, but DIABLO cannot handle any missing values whatsoever. So you'd either have to use some way to impute the missing values, or you have to remove any variables that have missing values in them. Can't handle. na.omit means remove rows with missing values. Parentheses, and this one is called transcriptomics _log2_z. So I'll just type in the first few letters of that and then hit tab to autocomplete. That creates our list that we're going to call data. Rebecca, did you have any luck with the installation over there?
No, look, so I'm online.
Okay, sorry about that.
It's okay.
Yeah, so we'll run that. And then we're just going to check our data to make sure it is in the format that we think it is, or that it should be. So lapply means apply a function to every element in a list. And we're going to take the data list and we're going to apply the dim function to get the dimensions of every single matrix within that data list. It'll give us 3 dimensions. So yeah, each one of them has 18 rows and variable number of columns. That's correct. So we're good there. Oh yeah, there was some missing values did get removed from the metabolite data. There were 170 before. Now there are only 94 because some of them had missing values, and I think a few of the transcriptome ones got removed as well. So we've kind of used a quick and dirty way of cleaning up missing values by just deleting any features that had any missing values in them whatsoever. And another real important thing to check, and this is stuff that has messed me up and other people up many times, is like if you have multiple data sets that are all supposed to be arranged in the same order, so that like column 1 or row 1 of transcriptome should be sample 1 and row 1 of metabolite should be sample 1. It should be in the same order every time. If they're shuffled around, you're going to get the wrong results. And I mean, it's happened to anyone, I'm sure, who's done this kind of thing before, that like you'll do a whole analysis and realize that things were mixed up and that's why you didn't get the results you thought you did. So we're going to check the row dot names of every single element in data and just make sure they're the same. If they're not in the same order, we would have to go in and mess with that. So yeah, you can see that they're all in the 0 hour 1, 0 hour 2, 3, and the 4 hour 1 through 6, 24 1 through 6. Everything, if you look at it, is in the same order. So we're good there. Very important not to skip that step of checking that. Now, if you remember that DIABLO is a method that is a supervised method. So it is not only looking at patterns across the omics, it's looking at them associated with some outcome variable. In this case, it's not really an outcome, it's our treatment, it's our time point. So we want to know, are there patterns in the data that go across multiple omics that also explain the maximum amount of variation between different time points? So we need to have a Y variable. All the different omics are like our X variables, and our treatment is our Y variable. So we're going to create a vector called Y. And this will basically rep 0, 4, 24, each equals 6. We'll make a vector that's 18 elements long with 6 0H's, 6 4H's, and 6 24H's, since that's the order it happens to be in the data. Yeah, really, we should have used like some sort of rep thing to make sure that it was the same, but all our data is already organized in order, in increasing order by time point. So we'll run that line. Now, yeah, Y is a factor with 3 levels. It's 18 elements long. Now here, our next step is you might want to get the gene annotations for the transcriptome data. This is the only thing we're using that the mouse annotation database package for. But yeah, we're basically going to, since right now they're just in ensemble ID, which is like a long numerical ID, we're going to replace those with the symbols. So that's what this does. And then you can kind of, then this next couple lines of code will get rid of any duplicate IDs, and then replace it with the replace the column names within the transcriptome part of the data with those actual annotation IDs instead of numerical IDs. That's what this code is doing. It takes a second to pull that from the table. Okay, so the next thing that now, yes, basically we're going to do multi-omics integration now. And what we need to do first is basically DIABLO is based on a partial least squares framework, which is a type of multivariate analysis that is supervised. It has predefined groups that each data point belongs to, and we're going to do this in a multi-omics way. But first, we want to do a pairwise partial least squares on each pair of, we have 3 omics data sets, so we have three possible combinations of 2 in there. And what we want to do is look at what is the correlation of the between each, basically between the PLS axes for each of the pairs of omics in a one axis PLS, to see if they are what is their correlation, and we're going to basically pass those values into our DIABLO model. And the basically DIABLO requires you to pass in a design matrix which has the pairwise correlations between each omic. And the correlations basically can be between 0 and 1. If DIABLO can kind of have 2 goals. One would be descriptive, to describe as much variation as possible within the data set. And the other would be predictive. Predictive would be if we are trying to use the relationships in the omics to predict some outcome. If we're focusing more on prediction, we would want to put lower values in the design matrix for the correlations, which will sort of feel like prevent against overfitting. It's kind of like regularization in machine learning, where you would sort of not fit the data quite as closely so that it was better able to predict new values, versus if you use high correlation values, it will fit the data more closely and pull out more information that's in the data at the expense of not being able to predict new data as well. But since this is not really a predictive scenario, we're just trying to look at the effects of treatments in this data set. We're not trying to like predict what time point different omics data belong to later on, we will probably want to put higher values in the design matrix for correlation. But we can also use a data-driven approach to look at what the correlations are between each pair of omics, so we'll know what to put in the design matrix. So that's what we're going to do right now. Using the PLS function, which is partial least squares, that's in the mixomics package. And we're going to do that between each pair of elements in data. So we're going to do one for transcriptome versus metabolome, transcriptome versus protein, and so forth. Yes, Peter.
Oh, I just have a quick question.
Yes.
So I was wondering like what you meant by like higher or low correlation. Shouldn't the correlation be the same, like when you calculate it?
So it's not what the correlation actually is. It's a kind of like tuning parameter that we're putting into the model, basically.
Like a weight?
Yes, exactly. And so that's what we're going to try to figure out what a good weight is to put in there.
Like, it's not the actual correlation of the data sets, it's the correlation between the components, right?
That's right.
So not, yeah, so like, you'll see like either like a really high, but if you go and do like an actual correlation, they probably aren't.
That's right. Is the correlation between the first component of a partial least squares from each pair of data sets, basically. So we're going to do that for the transcriptome versus metabolome first. And so we're going to do double brackets, which means get that element from the list and then quote. We're going to get the element called transcripts from data as our first, as our sort of X variable in the PLS. And the Y variable is going to be the metabolome element from data. Bracket, bracket, quote. And we called it metabolites, if you remember when we made the list called data. So it will take that one out. And number of components equals 1, because we're just looking at the correlation of the first PLS axis between the two, the one that explains the most variation. And we'll run that for all three. Highlight the whole thing and hit Control Enter. Transcripts versus metabolites and so forth. So yes, this is kind of like this is just kind of a preliminary step to figure out the weights or hyperparameters that we're going to pass to the DIABLO model. You could probably like, even if you were really like anal about it, do some sort of cross validation to figure out the optimal ones to put in here, but that's like way overkill for what we're doing. That's like, if you really cared, you could do a cross validation to optimize this value. But we're just kind of like, I tried out different ones and honestly, the results were basically the same every time anyway. So I'm not even sure how much difference it makes in practice, at least in this case. So yeah, then let's just look at what those correlation coefficients are. We're going to use the core function. That means get a Pearson correlation coefficient and print it. And so PLS1 $ means it has an object in it called variates, which are basically the axes. $X. This is like the scores for the transcriptome data from the first pairwise PLS, and then we want the scores for the metabolome. And what is their correlation? Variates $Y. Oops, $Y. A capital X and capital Y. What is the correlation there? Run that. It's 0.98. The next one, run it. It's 0.95, and this one is 0.92. So they're all very high. So this indicates that if you like pull out the one axis that explains the most variation in each pair of omics, they're very correlated. So like there's probably a similar signature, at least with regard to transcriptome, metabolome, and proteome in each of the three. They're sort of have similar patterns of variation. So the correlation is high. That means we can get away with putting high correlation value in the design matrix. And so, yes, the next thing we're going to do is generate that design matrix. So I decided to put 0.9 in for all the pairwise correlations because they're all at least 0.9. So our lowest one is around 0.9. So I put 0.9 in there. So I make a matrix that has only values of 0.9 and number of columns is length of data, which is 3. Number of rows is also 3 length of data, and we're giving it row and column names of transcriptome, metabolome, and proteome. Run that, and then we're going to set the diagonal of that matrix using the diag function to 0, because we only want the pairwise, the design matrix has 0 on its diagonal. That's just the way that it's set up. We'll run that. Then we'll print design. If you did it the same way as me, you should get this. So each pairwise correlation weight in the model for every pair of omics is set to 0.9. Again, we could use a more rigorous way to figure that out and get the weights, but it would take even longer to do the model tuning if we also had to cross-validate for that. Okay, so now the next thing we're going to do is, we're actually going to fit a DIABLO model. Now, if you recall from yesterday, what a DIABLO model is based on sparse partial least squares discriminant analysis. What does that mean? Basically, partial least squares is trying to find a low number of dimension axes that will explain the most variation across a multivariate data set associated with some outcome, which in this case is our time point. We want to find to sort of condense down the information in our many dimensional data set into a few dimensions that are maximally associated with time point, that differentiate the time points as well as possible. And basically, DIABLO integrates that information across all the omics that go into it. And it's called sparse partial least squares because it will not only will it reduce the thousands of dimensions down to a few, it will be sparse. It will allow many of the values in those few dimensions to be 0. So it'll even condense the information down even less and still preserve as much of the original variation in the data set as possible. So basically, the model not only will have a certain, but we have to specify how many components, how many dimensions we want. And we also have to specify how many non-zero values will be on each component for each of the omics. And how do we know what to put, right? Like basically we have to use cross-validation to tune the model and decide that. Does anybody has heard the term cross-validation before? Okay, Peter, can you say what is cross-validation?
So it's like where you leave out some of your data. You don't train the model on that one bit of data, and then you use that to test the model to see how well the model performed. And that's done so that if you overfit the model, then the model will learn like all of the sort of statistical artifacts that aren't really meaningful. And if that happens, then the testing will tell you that it's not actually good at predicting, even though you might have a high correlation value.
Yeah, you don't want to fit on your noise. You want to fit on the actual signal in the data. So here, hopefully people on Teams can, if the camera will follow me, I can like write on the whiteboard how that works exactly. So basically, in cross-validation, like here's your data, like a matrix. Let's say we did 5-fold cross-validation. We would divide the data up into 5 pieces, and then 1, 2, 3, 4, 5. First, so we want to know what parameters we should use to fit the model. First, what we're going to do is take data set piece 5 and set it aside and fit the model only to this part of the data, never letting it see that part. And then use the model that was fit to this part to predict the values for data set 5, for that 20% of the data. Then we do that again, excluding data set 4. So we'll fit the model to 1, 2, 3, and 5 and use it to predict 4. And so forth. So we actually have to fit the model 5 times. By the time we do that, we'll have a predicted value for every single point in the data set, but the model that predicted it never got to see that data when it was being trained. So it like Peter said, prevents you from getting a model that's capturing like noise and random like stuff that's not actually the signal that's found in the test data set. So basically we would, to do cross-validation to decide the optimal number of parameters in the model, we would have to repeat this procedure of fitting the model to like chunks of the data many times, each time using different number of components. Like, because that's the thing we're trying to figure out. Should our DIABLO model have 1 axis, 2 axis, 3 axis, 4? So we'll have to repeat this many times, once for each of the, repeat this 5-step process once for every combination of parameters we want to test and see which one has the best prediction performance on that data that it never got to see. And that will tell us what is the optimal number that has the best prediction performance without overfitting. That's cross-validation. Very important for any type of machine learning approach. So if you ever get into machine learning, you'll see that. So the DIABLO function is, for whatever reason, not called DIABLO. It's called block.splsda, sparse partial least squares discriminant analysis by block. That for some reason they also call the multiple omics that go into a multi-omics integration blocks. I don't know why, but that this package mixOmics called them blocks. And yeah, block SPLSDA. And the X variable we're putting in is data. So right, data is actually a list of 3 matrices, one for each of the omics. So those are all our X variables. Y was that vector we created a little bit ago called capital Y. Number of components, well, I put in 4 because that will test everything from 1 through 4. The reason I didn't put an even higher number is because we have 3 time points. Usually 2 components are going to be enough to differentiate between 3 time points. Like they're usually like the number of different groups you have -1 is a decent guess for how many components you would want. But just in case a little bit more is needed, I threw 4 in there. So it'll test everything between 1 and 4. You could make it higher if you want. And then the design matrix is the matrix called design we created, which has the 0.9s and stuff in it. So now we'll fit that. So run that. Design matrix has changed to include Y. Each block will be linked to Y. So that's just standard text that comes out, showing that we're not only looking at correlations between the omics, we're also looking at correlations between each omic and the time point variable that we created. Now we have to tune the model using cross-validation to determine the optimal number of components. And the way that is done is the function perf. PERF stands for performance. We're going to use the model we just fit, and what validation method are we going to use? We had to put in quotes. You can use single or double quotes in R. It doesn't matter which one you use to create a text string. M-fold, capital M, that means cross-validation basically. Cross-validation with M folds. Folds are what you call the different chunks that we break the data set down into. Those are called folds in cross-validation language. So I should have mentioned that before, but and I'm just going to do 3-fold cross-validation because it's a little bit quicker. So why that happens? Sometimes that happens on this demo server that even though you're using it, it falls asleep. So yeah, we're going to do 3-fold cross-validation, and also it's useful when you do cross-validation to repeat the entire the entire cross-validation procedure many times. Just in case the way you broke down the folds is chosen randomly, just in case you got particularly lucky or unlucky with one random split, you should repeat it a bunch of times. So I'm gonna repeat the procedure 10 times. So basically we're fitting the model 3 times to different subsets of the data for each number of components from 1 through 4, and we're repeating that whole thing 10 times. So we're basically fitting the model 3 times 4 times 10 times, whatever that is, 120. And I set a random seed to just some number 1, 2, 3, 4, so that should ensure that we both, or that I and you get the same results, because cross-validation is based on a random split of the data. So we should get the same results if you do this the same way as me. So we'll run this, and it will take a little more time because we're fitting the model a bit more than 100 times. So it will take a minute. But after we do the cross-validation, we're going to make a plot to look at how well the performance did for each number of components, and then look at what it decided the optimal value was. So yeah, this is procedure that you would do if you were doing DIABLO on your own data. You would need to do this. We'll do a few more minutes and then we'll take another 5-minute break. Never have too many breaks, so. Yeah, basically the rest of this lesson is there are some more tuning steps that we're gonna have to do to select other parameters that are gonna go into it. We're gonna do all of that. Then we're going to figure out the optimal parameters, fit a final model using all those optimal parameters. And then the rest of the time, there are many different plots and graphs and tables and things you can make. So the rest of the time, we're just gonna make a whole bunch of them and look at them and talk about what they say. And because those are the kind of things that would go into a publication. So yeah, we're tuning the model to determine the optimal parameters. We're fitting the model with those parameters, and then we're gonna just play with the output of it. That's what we're gonna do for the rest of the time. Okay, so mine finished running after a minute or so. Now that it's done running, now we can make a plot using the plot function, which has a method for this particular object. So here we see the classification error rate is on the y-axis, and the number of components is on the x-axis. And we have 3 different distance metrics. Basically, what DIABLO is doing is it is using from cross-validation, it's taking the model fit to the other part of the data set that was not held back and using it to predict which time point the remaining data points that we didn't use to fit the model belong to. But it doesn't just give a prediction of what it belongs to. It gives like a score for what probability it is to belong to each time point. And then we use sort of like a distance metric to decide and which time point each belongs to. But there are different distance metrics you can use for that. And so this is just like to check which whether they differ in their results. And also you can see that there's balanced error rate and overall error rate. What that means is, let's say not all outcomes are equally likely, right? Like, let's say you're a weather forecaster in the desert where it only rains like 1 out of every 100 days. You could have a very simple model that just always predicts it will not rain. You would be right 99% of the time, but it would be basically not a useful model, right? Because it could never even though you're right 99% of the time, you could never predict rain if it would happen, right? So, but if it rained 50% of the time and you always predicted it would not rain, you would be wrong a lot more often, even though it's the same model, right? So like if your data is imbalanced, you can't just look at how often you were right. That doesn't tell you if it's a good model or not. You have to account for if it's imbalanced. But our data set has exactly 6 samples from each time point, so it's perfectly balanced. So the balance error rate is exactly the same as the error rate in this case, because we have 1/3, 1/3, and 1/3. So you can actually see that there's like some dotted lines and solid lines, but they're right on top of each other. So in reality, you will have many data sets that are not balanced in that way, and you will have a difference there. And so you want to use the balance error rate to correct for the imbalanced data. That's just an aside. Here, we don't have to worry about that. We also see that the error rate is basically up to 30% for this max distance metric. When you only have one component, it's already like pretty close to 0. Yeah, the omics are able to predict what time point these things come from, even using only one component in DIABLO. But by 2, all the distance metrics are down to 0 or nearly 0 error rate. We can also look at pull out from the performance object. There's an element in that list called choice and comp for what it chose as the optimal number of components. And within that, there's another element called weighted vote. Yep, so we'll should have a capital W, weighted vote. Weighted vote, there we go. Run that, and so this tells us, if we're using overall error rate as the criteria and maximum distance as the distance metric, 2 is our optimal number of components. So the error and balance error rates, since they're the same, they agree in each case. Apparently, for Mahalanobis distance, it said 4 is the optimal number of components, which I'm not really sure why it says that, because the error rate looks pretty close to 0 already for 2 components for it as well, but I guess it's still a bit higher than 0 there. So, but I think my intuition to begin with was that 2 would be a good number of components because we have 3 time points, and all the distance metrics give a good performance at 2, so we're going to go with 2. But as you can see, there's not perfect agreement there. Okay, now the next thing we have to do is, now that we've decided we're going to have 2 components, we have to tune the model again to decide how many features are going to have non-zero scores on each component. And basically, the only way we can figure that out is by trying out every possible combination with each of the 3 omics, how many features to keep. And I said, well, we'll try, a bunch of small numbers and go all the way up to 50. We can allow up to 50 variables from each omic on each component to have a non-zero value and to contribute to our DIABLO predictions. And we're gonna that's why this cross-validation step took an incredibly long time to run on my laptop, because we have like 10 or 12 different combinations here, 10 or 12 here, 10 or 12 here. So it's like 1,000 possible combinations there, 10 times 10 times 10. And then for each of those, run the cross-validation, so fit the model multiple times for each of those combinations. And then you really should repeat that whole thing multiple times. So it would take, basically, if you would do this, you can, you would run it on like a high performance computing, probably, if you didn't want to, it would take, you can also set it up to run in parallel on your own laptop and use multiple processors basically on your own computer, which would speed things up. But if you have a big omics data set, you probably need to do that. Like this is, it can run on a laptop. It will take hours, but it can. So yeah, just either like let it run overnight or run it on a cluster, basically.
I think,
Yeah.
most of the time, like once you're happy with whatever you've tuned, and when you're done with DIABLO, save it. Like,
Yes. Oh,
Do
yeah,
not have it to where you have to rerun it every time. Just like make another notebook to do your plotting. Or
that's
something
right.
like that.
Save the, yeah, so that's why yeah, this is where, if you go back up to the top, where we loaded this Diablo tune multi.rda, I saved the output of the tuning of this step, and because I'm not gonna run it on here, especially the demo server is even less computing power than a laptop because it's just for demo. So we are not gonna run it on here. It would take hours. So I just want to show, you don't really have to fill in the blanks for this part. I'll just show you if you don't want to, because we're not going to run this anyway. These are the combinations we're going to test, and you can see it's a list, and the names of that list should be the same as the names of the list of the data. So it matches them up. Transcripts was the name of it. Yeah, you can, if you go into data here, you can see what the names are. Yeah, there's transcripts, metabolites, and proteins. That's what we're going to call these two. So yeah, we would run that, and we also tune multi is what we're going to call this object, and there's a function called tune.block.splsda, which is used to tune a Diablo model. So remember, our data here is our list of 3 matrices. Our Y is a vector containing the time points that each one belongs to, each data point. And you remember, we're using 2 as our number of components, which we decided already from a previous tuning. Now we're going to test every combination of number of features to keep on each component using our design matrix, 3-fold cross-validation, all repeated 10 times. What distance matrix are we going to use? Distance metric are we going to use to assess the model performance? Remember, we had Max, Centroid, and Mahalanobis. I noted here that Centroid was always, the best or tied for the best of performance. So I'm going to use Centroid's distance as the distance metric. Not really exactly sure what that is, but I just know it performed well, so that's why I'm gonna use it. And then I set a random seed to get reproducible results. So yeah, that's how I run that, but don't run it because it will take all day. So now we can pull out because you can see that where is it? Tune multi is already in my environment because I loaded it before where I saved it when I ran this back at home before I came here. So tune multi contains various things in it, but one of the elements it contains is called choice.keepx, which means what are the optimal number of variables to include from each omic on each of the 2 components in our final model. We'll run that, and then we'll make a new object called list keepx, and then we'll print that. So you can see that transcripts 40 and 1, metabolites 50 and 1, proteins 1 and 2. So just what that means is that it found that 40 variables from the transcriptome should have non-zero values on the first component, 50 on the 50 metabolites on the first component, only 1 from the proteome, and then actually very few on the second component. So it seems like hardly any, in a way, 1 component is almost adequate, and there's only a little more information that needs to be added from the second component to optimally separate the time points. Yes.
Why on the first component did it only give 1 protein?
I really don't know. I guess like the information from the other 2 could have been redundant, and because all this is correlational, right? Like it doesn't know why these things are predicting. To them, it's just numbers, right? It's just so like if information is already conveyed by the first 2 and I don't know if it prioritizes the order based on how it's put in or anything, but yeah, it just, as it turns out. Also, in a way, I maybe should have even put 0 as an option here, because if it went down to 1, it might have also gone down to 0. And you can see this one, is 50. The maximum I put was 50. So really, it could be even more. So maybe I should have. I didn't. Yeah. If I was doing this for like a publication, I would probably put in. If it got to the maximum, I'd probably add even more and repeat the cross validation for even higher than 50.
Yeah, that's right. You said like you can kind of guess by the total size of the feature.
Right, but there was only, the reason I didn't bother was because there was only 90 metabolites. I was
Yeah.
like, well, 50 is already like more than half of them, so.
Yeah.
So for whatever reason,
Surprisingly.
yes, that was odd, so, but I was like, I'm not gonna run this again, because this is just for learning, so I didn't bother to like redo it. But I should have, if I was really doing this for real. Yeah, I think that's, a decent stopping point for us to take another 5-minute break. 13 at 11:31, where we can then just make plots for the rest of the time. Yep. All right, I just realized my clock is not the same as everyone else's. I don't know why the clock on this computer is slow, but I think it's been about 5 minutes, so we'll keep going here. So yeah, like I said, it's now we've kind of gone through all the steps of tuning the model. In other words, choosing what parameters the final model should have. And so now we just have to fit the model one last time, not thousands of times, just one more time with all the parameters that we decided are optimal. And then that's our model. And we can then look at its output, make plots, see if you can tell any stories based off of it. So let's go ahead and do that. So we're gonna call it final DIABLO model, and then we're gonna use the block.splsda function again. So that's one that just fits a single DIABLO model, not doing tuning. Remember, our data is our list. You know, it's all the things we figured out. Our two components we figured out was best, and the list.keepx, that's what we just got from the cross validation we did, showing how many non-zero variables, and then the design matrix that we used the pairwise PLSs to decide that 0.9 was a good correlation to put in. So we'll run that final model, and it should only take a couple seconds because it's only fitting it once. Now we can then look at which actual gene names and protein names and metabolite names were the ones that the model said are important for differentiating between the time points, and that are both related to the other omics and related to have differences between the time points. That's what DIABLO is telling us. We can pull them out using the function select var with a capital B that will pull out the variables and which block it comes from. In other words, like I said, DIABLO calls the different omics data sets blocks, and those are they have names based on the names of the data that went into it. So one was called transcripts, and component equals 1 means the first of the two axes. $transcript, $name is the item within this very complicated list object that contains the names of the variable, the transcriptome, the genes from the transcriptome that are found in the final model for the first component with non-zero values. So here they are. You can see most of them have annotation. One of them didn't have an annotation. It just has its ID from before. And yeah, so yeah, you can run the same for the metabolites. Those are the 50 metabolites that have differential abundance between the time points and also are related to patterns in the other two omics. Yeah, and then the protein, there's just one protein there. Yep, oops. And then you can do the same for component 2, but remember there was only a very small number of variables that were retained in the final model there. So those are just ones you can look at. Yeah, so now the rest of the time, we're just going to go through some of the plots you can make, some of which you might want to put, some of which are kind of more just diagnostic to make sure the model works, and some of which actually show interesting things that you would want to put in a manuscript to actually talk about. The first one is more of a diagnostic plot. It doesn't really show much interesting. It just kind of confirms that the DIABLO model is pulling out correlations that exist in the data, called plot DIABLO. And we'll show the first component, ncomp equals 1, and then we'll use our color scheme that we defined previously so that all the plots have the same colors. So yeah, this basically, it just shows that it's kind of like it shows the very big number, the pairwise correlations between the DIABLO axes, basically for each pair of omics, which are high, as we found when we did it just pairwise between them. And then it shows the how the data points cluster using, transcripts on the y-axis, metabolites on the x-axis here. You can see that the time points, the data points from within each time point are similar to each other in all of the axes, all three of the omics data sets. Although there is some overlap there between the 4 and 24. And let me see if we can do this for component 2 as well. I'm just going to change the 1 to a 2 here and see what it looks like. Yep, so there's component 2. And you can see that here the on component 2 is kind of pulling the 24-hour time point apart from the other two, whereas component 1, if we go back, is pulling apart the 0 from the other two. So that's like 2 components is kind of adequate to separate 3 groups, because the first one separates one and the second one separates the other, so then all 3 are separated. But this is not a very super interesting plot, because it doesn't really show what's going on in terms of the, it just kind of confirms that the model works, basically. And but what can we do? We can start to look at scatter plots of the individual data points, the samples, by each pair of omics. We're going to use the plot indiv function for that. And we're going to use our final DIABLO model. We want to make the plot from that. And then there's different arguments showing what how the plot will be made and what the title will be. Run that. So yeah, here we see the this is somewhat similar to the previous plot, where it shows for the first 2 components. By default, it shows the first 2 components, but our model only had 2 components. How well the different data points are clustered. The DIABLO model was able to pull out the variation between the time points and split them apart. Because again, we have a pretty strong signal in this data where the gene expression and metabolite composition is changing quite dramatically over time in these cells. So we see a very strong signature. And it's also interesting, you can just visually see that each of those 3 panels looks more or less the same, right? And that indicates that there's similar patterns of variation in all 3 of the omics. And you can also look at that by looking at an arrow plot, which kind of combines all 3 of these into one plot and shows how consistent the clustering is across the 3 omics. So I'll show you that and explain it in a second. Plot arrow is the function there. And again, our final model is what we're using as input. What does it look like? So yeah, here you can see that each of the 18 data points, instead of just showing up once, is shown by a center point with 3 arrows going out of it. And each of the 3 arrows is where that point is placed on a scatter plot for each of the 3 omics. And so if the arrows are short and all 3 of those omics are close to each other, that means the omics have very similar patterns of variation between them. Yes, and so if it's far apart, they don't. So basically you can see that it just helps illustrate that the clustering is the same across all 3 of the omics, so that there's kind of like correlated variation across all 3 omics, which again, we saw by having very high correlations with one another. There's a correlation circle plot. plot var is that function. And here's a bunch of arguments to change the size of the points and their shape and things like that. So let's take a look at what does this show. Every symbol on this plot is one of the variables, like one of the transcriptome genes or one of the metabolites that was present in the final model with a non-zero value. And how highly correlated are they with component 1, dimension axis 1 of DIABLO, and component 2? You can see that all the ones that were retained are near positive or negative 1 on one or more one of the axes, because you know, all the thousands of transcriptome genes and proteins that were not correlated would have been around here, around 0, but they were excluded from the model. They dropped out of the final model, so they don't show up here. That's why it sort of shows a donut. You know, absolute value of the correlation is greater than 0.5. The metabolites don't fall out quite as cleanly. Somehow, I don't know why the cross-validation did this way, that, you know, many that didn't have a super high correlation were retained in the final model anyways. So maybe there's a little more noise in the metabolome data, but the transcriptome genes, the ones that were kept, are extremely highly correlated, either positive or negative, with the first DIABLO axis. And that makes sense, right? Because the transcriptome, we kept 40 from the first axis and only 1 from the second. So most all of them are correlated with axis 1, but have a low correlation near 0 with axis 2. So that makes sense because they were retained on axis 1, not 2. Does anyone have any questions about any of this so far? We're doing a few more plots, and then basically we're done. So we're kind of heading to the home stretch here. And I'll let you go early, you know, or you can ask me questions for a while, but either way. The next plot I'm going to show you is actually probably the most complicated one, but for some reason they put it in a lot of papers that are made that have multiomics integration or DIABLO that was used for. It's called a Surcos plot. I kind of think they're confusing and have more information than really is necessary for a good visualization, but some people think they're cool. And so even if you don't put them in a paper, you'll probably see them in a paper. So it's good to know what they are and what information is in them. So we're going to make one, and I'll try to explain what it's showing. It's called Surcos plot. And you have to set, basically the Surcos plot shows pairwise correlations. Part of what it shows is pairwise correlations between variables from different omics. And it will only show a pairwise correlation above a certain threshold so that it doesn't show every single line. So I have set the cutoff. You can set it to whatever you want, but I decided, just based on testing out a few different values, that 0.97 was a good cutoff. That's a pretty strict cutoff, right? Like the correlation can only be between -1 and 1. And so the absolute value has to be greater than 0.97 for it to show up on the plot. So, and then there's a bunch of other arguments, which I didn't write this code, someone else did, but it's like what the size of all the data points are and that kind of thing, how they should be labeled and so forth. So let's look at that. So yeah, it's like, whoa, that's a lot. What the heck is that? But this is a Surcos plot. What does it show? Well, okay, you can see here that there's basically a giant circle with a bunch of little segments going around it, which are the variables from our omics data sets that were retained in the final model on one or more of the components. And so our like proteins, there was only like 1 from the first component and 2 from the second, so there's only 3 proteins. The transcriptome was like 40 plus 1, and the metabolome was 50 plus 1. So first of all, it shows those, and then in the middle are all these weird lines connecting pairs of variables from different omics that are correlated with each other above 0.97. And if they're correlated at positive 0.97 or more, they are in a purple line. And if they're correlated at negative 0.97 or more, they are black. So then you can see like acetoacetic acid concentration in the cell is positively correlated with a bunch of transcripts from the transcriptome. And it's negatively correlated with a number of them as well. That's what that shows. And then there's also these lines going around the top, which is, let me maximize that so you can see the whole thing. For some reason, the legend is slightly cut off here, but these are the gene for like the relative abundance at 0, 4, and 24 hours shown in 3 different colors. You can see there's like, it's almost like an axis. You can't see the y-axis because it's all just normalized to have the same min and max. But like these, like for example, this transcript was very abundant at time point 4 and 24, but not very abundant at time point 0. And so it's like, well, those ones were the ones that were retained in the model for axis for component 1, because component 1 is the one that differentiated time point 0 from the others. So like some are really abundant at the other time points besides 0, and here are some that were very abundant at time point 0 and not so much at the later time points. And a few that are kind of in between. So yeah, it's like, well, then the ones that are really abundant at time point 0 have a positive correlation with the metabolites that are really abundant at time point 0. So yeah, that's kind of what, yeah, I mean, if you look at it, it's really not that complicated, but if that thing just pops up in front of you, it's kind of scary looking and you're like, what the heck is this? So yeah.
So what you can do, the problem with the surpass plots is that you would ideally, you won't want to see the features that are not correlative.
Right.
And that when you do your cutoff, they don't cut them out. So what you can do, you can store the plot function into a variable and it will give you a correlation matrix. And then you can plot that.
So like,
instead of
you
using,
want to just like get rid of all these ones because they don't have any lines coming in or out of them, and then that would simplify things down a bit.
yeah, so
Yeah.
it scrunches it down, and then like
Right.
these will all end up on your plot loadings anyway, because these are
Right.
the selected features.
Right.
So if you're interested in plotting and making the plots cleaner, that's the way that you can get around it, is plotting it yourself, unfortunately.
Yes, because yeah, I mean, and you may have a much smaller number of features as well, depending on how your model shakes out. So if there's only like 10 around this whole circle, then it wouldn't be a problem to show all of them. But this one ended up with about 100, so it's quite a lot going on. So that's a Circos plot. Yes, we have a few other kind of plots. The loadings plot is one that shows which particular variables have the highest association with each of the components. And so we can look at which ones might be, these are the ones that sort of have the biggest difference between the time points, and these are the ones that maybe are meaningful to talk about. Plot loadings is the name. Okay, and so we have to choose a bunch of different arguments to decide how the loading plot is made. First, we want component 1. And we're going to do this for just the transcriptome first. You can do it for other ones as well. Contribution equals max. It will plot only the ones with the largest loading, basically, and it will use and method equals median. I believe it's because it will for each variable, it will show the time point that it is most associated with. Yes, I can't remember exactly how the max and median play into that. I think I wrote this some text about it in the lesson text you can refer to if you want a more detailed explanation. But I can't remember off the top of my head. But we'll look at the plot, maybe it will make more sense. So yeah, this shows, here's the loading plot for component 1 for transcriptome. You can see that basically if, oh, that's right, if they're colored by the contribution equals max means they're colored by the time point that they are maximally abundant on. So like, and component 1 just happens to have negative values when variables are more abundant at time point 0 and positive when they're abundant at time point 4. So basically this means that like gene DGAT2 was had a very high loading on component 1 because it was very abundant at time point 0 compared to the other time points. And MNP11 was very abundant at time point 4. So it has a positive loading on axis 1. And so it only shows the top ones. That's what that plot is. And we can also look at it for metabolites. And we get kind of a similar look because a lot of metabolites apparently were very abundant at time point 0 and not so much at the other time points. Yes.
I just have a question. Why do you need the DIABLO integration for this?
Yeah, I mean, this probably would, yeah, it probably could give similar results if you just did a single omic analysis, and it would most likely show the same thing. I mean, I guess these are ones that not only have the biggest difference between the time points, but also high correlations with the other omics. So it's going to show both. But in many cases, those would be similar, especially with this sort of simple data set that we have and just has time points that we're comparing. Yeah, but yes, I mean, a lot of different approaches if you have a really strong signal in your data and really a lot is going on, the overall conclusions you draw should be consistent regardless of what method you use. Right, it would be like a red flag if you analyze a data set in different ways and got totally different overall patterns each time. That would mean that like your data set has a lot of noise. But like if you have a real strong signal, it doesn't matter how you look at it, you're going to get like the same. Like if malic acid is like real important, it's going to come up no matter how you analyze the data. If you do, neural network, if you do a linear regression, if you do DIABLO, whatever, it's going to come up as important because it really is important, right? So like you would hope that if there's a true signal that it would come out like in any method you use. And so yeah,
it's not causal. There's nothing.
That's right.
Causal. So but you probably could say like, hey, you want to get closer to saying like, metabolite X can affect gene X and then leads to
That's right.
protein X, but this isn't going to tell you like, how this happens temporally.
That's right.
And it's not going to tell you like what intervention causes this, but you can get closer to that. I guess you could start forming
That's right.
things around
this is an exploratory approach to generate hypotheses that you can later test. Like, right, malic acid might be just like, it might be involved in a pathway that's like important for this stuff, or it can be like a byproduct that has nothing to do with it, or it could just be like statistically correlated with the things that are actually doing stuff, right? It doesn't tell you what's actually doing stuff. It tells you patterns and it lets you draw pictures and tell stories that, like, if you really want to mechanistically test if malic acid is doing things, you'd have to do like an experiment where you literally manipulated the malic acid and saw what happens. That would be like or like go out from that. I just picked that as a random example, but like you could like go and from the outset like measure that and see in more detail. Yeah, it's an exploratory hypothesis generating, but not hypothesis testing framework.
best case scenario, you did this and then spun something off of it, and then
That's
like,
right.
oh, I found this at the bench.
That's right. Or you're not, or you don't even care about what's doing what. You just want to make a predictive model, like use multi-omics data to like predict the likelihood of getting disease or something, and then you wouldn't even care. As long as like you can measure these same things on other subjects and then predict their outcome, that's what you want. So yeah. And in that case, right, like if prediction is what you want, you don't even care what method you use, DIABLO, single omics, whatever, you use whatever gives you the best prediction. Like if you're in it to make money, you're not gonna like care how, you just want the one that has the best prediction performance, you know? If you're like in industry and are like a heartless person who only cares about money, then you just like want to just like use whatever model works best. But we're in it for science and want to learn, right? So yeah. Yes, but prediction is still important even if you're in science, like in basic research. Okay, so a couple more plot, actually just one more plot, and then one last evaluation of the model performance, and we will be done. So I wanted to make a heat map, similar to the ones we made for the single omics data set. So first I defined a color palette, which goes from red, blue to red, just so you can see like low versus high expression. And then the heat map function is called CIM DIABLO. And the final DIABLO model is the one we're going to run it on. And if you scroll over, you can see all kinds of arguments that were put in just to like define the color scheme of the all that stuff's not really necessary, but it just defines the color scheme to look the way we want it to. Oh, and it doesn't work because we don't have a big enough window, but that happens on this small screen here. But if I make this bigger, it should work, at least temporarily. If you're doing this on your own, you should be able to see it, but try that. It's still too large.
You could save it to.
Yeah, let me see if I can. Let's see. No, that's not going to work. Let's make it even bigger. Yeah, if this doesn't work, I'll save it to an image. Dang it, still didn't work. Let's see. Yes, so this is really, hopefully you all can get the plot to show up on your own and not get this error, but I'm trying to do it on a real low resolution screen here. No,
It's showing us that.
you got an error too? Yeah, let's see. Yeah, you can try to like blow up your plot window too and see if that helps. Let me just, yes, I didn't, let me just move this over to my other screen, which has a better resolution, and try to do it.
Yeah, you can, do the PDF and then move that off.
Yeah, I'll have to do that.
Sure.
That's gonna be, yeah, I don't know why it's, yeah, I think it's something to do with the, I reduced the margin, but that will help. No, that doesn't work either. Okay, let's see. Well, I'll make that heat map in just a minute. Let me just show the other thing first, and then I'll tinker with getting that to show. Because yeah, this happens when you do it on this if you're just trying to like make interactive plots on the demo server. Sometimes it won't do it. I'll do that in just a second. But yeah, the last thing I wanted to do before we're going and trying to play with showing the heat map is to basically evaluate performance of the final model and see how well it predicted the time points from the original data using one final cross-validation step on the final model. And the rationale behind doing that, again, I said we're not really in this for predictive purposes. We are just trying to learn about patterns in the data, but even so, it's good to ensure that your model has good predictive performance, which means that it was a good fit to the data and the patterns that we, a model is not really the real world, right? A model is just like an abstraction of reality. So if our model doesn't go back to reality, it doesn't mean anything. So what I'm going to do is make sure that model worked well, basically. This is just a verification that the model more or less gives us back our data so that we can actually say the predictions that this model is making are meaningful. So we're going to use perf again to assess model performance, the perf function with n-fold cross-validation, 3 folds because we have a relatively small data set, 10 times repeated, and use that same distance metric, and then a random seed should be the same for, so we all get the same results. I'm going to run that. But I just realized I should have a picture of the heat map in the lesson text that, so I'm just going to go and show that instead of trying to like save it to a PDF, because that'll be a pain in the butt. So I'm just going to show you it in a second. Maybe just so you can show some of the different output this thing makes. Because I didn't have any trouble making the heat map on my own or on my own machine. It's just when you try to run on the demo server, it kind of screws things up. So this takes a second or two. Here, while that's running, I'll try to find the heat map and show it to you what it should look like. Yeah, okay, so here's the heat map. Now it got very stretched out, but yeah, so here's the heat map, and it just is similar to the heat maps that we've made before, except now it has an extra row across the top showing which of the omics each of the variables comes from, and then it's got 18 rows. One for each of the 18 samples, and about 100 little skinny columns, one for each of the roughly 100 variables that were kept in our final model. And it sort of, they're sorted, not necessarily by omic, but by how closely correlated they are to one another. So it seems like basically, and then we have a normalized abundance color scheme. So a bunch of the, and this is for component 1. So a bunch of the, mostly from the transcriptome and metabolome, have high abundance at time point 0 and low abundance at the other 2 time points. Then there's a smaller number of metabolites and genes that have low abundance at time 0 and high abundance at the other time points. Again, because component 1 is the one that separates those out. You could do a similar heat map for component 2 if you wanted. And yeah, so that's what the heat map shows. And again, it's like, well, you have to squint to see what the actual, I don't even think there's enough room on the axis to fit the names of all the variables. So it's only showing some of them. Those are like the names of the genes and metabolites down there. So that's the heat map. Sorry, I couldn't get the code to run live, but that was it. So now we'll go back to here. We can see our cross-validation has finished running. So let's look at the error rate from cross-validation, weighted, in other words, averaged across the cross-validation folds. What is it? Just to ensure our model did well. And so basically, if we only use one component, we got a 0 error rate. It predicted all the 0-hour time points correctly. It only had a 5% and 6% error rate on the other 2, overall 3%. but when we add another component, it goes down to 0 for 2 of them and 1% for the other. So then the average is less than 1% error. So that, yeah, that essentially confirms that the model is a good fit to the data and makes reasonably good predictions so that we can kind of trust its output. Yeah, that is all the material. Yes, it's, as you know, DIABLO is just one of the many ways you can do multi-omics integration. There's tons of other ways. This is kind of one of the simpler ones, and we've only scratched the surface, but I have to go home to my family, you know, at some point, so I can't stay here and always teach you about omics, even though also this is kind of the limit of my knowledge as well. So, you know, I can't, I wouldn't really be qualified to do it anyway. So that's that. And I'm happy we're done a little early, which is cool. So I'm happy to answer questions or just chat about things for the next little while before we go to lunch. Thank you all. And hopefully, thank you. People on Teams, thanks for, you know, participating, and I will stop sharing screen and stop recording. And yeah, anybody who wants to follow up on any of this stuff, please just email me or get in touch. Oh yeah, oh, I do have one other thing. Well, let me stop the recording first. I do have one other quick business item before